All right, welcome back. Today we're talking about finding limits analytically. Now, if I had to choose a particular section of chapter one that's the most important going forward for the rest of the class, it would probably be this. Okay, finding limits analytically. This is what we're going to have to use on a periodic basis throughout the rest of the class. So it's super important that we really get a good understanding of what it means to find a limit analytically, especially this box that you see on the bottom of the page right now, the properties of limits. We're going to use these throughout the class. So it's super important that you really internalize these properties, not just memorize them, because memorize them doesn't help you necessarily apply them. You do have to memorize them, but you also have to know how to use them and how to properly use mathematical notation and all that good stuff. So let's jump right in and see what we have going on here. So example 1.4.1 drives home the point that the numerical approach, and for that matter the graphical approach, to finding limits have pretty big shortcomings. For instance, if you do not know the graph of that function, then you cannot evaluate the limit. Okay? And even if you do know the graph, well, here, let's pull it up. Here, let's just type it in. Let's see here. I got Desmos pulled over here. So let's see. We have 2 square roots of x plus 2 minus 2 square roots of 2 over x. Okay, so there's the graph. All right. Now, even we have the graph there. Okay, clearly it's undefined at 0. That's where we're trying to find the limit. But now it looks like there clearly is a trend in the y values. Like there's no asymptote, like there's no unbounded behavior here. Clearly there is a limit because as we approach a 0 from the right and from the left, we seem to be approaching what, like about 0.7 or so from the left and from the right also, about 0.7. But here's the trouble. That's an approximation. Okay? We don't like approximations typically. Sometimes an approximation's fine, but almost always we are looking for an exact solution. And the graph here does not provide us an exact solution. Like it doesn't cross we don't have like the point, 1. We can't see that the y value is approaching 1 necessarily, or 1/2. Like 0.7, that's not a value that you would necessarily recognize. 0.7067. So that's a little bit above 0.7 and still a little bit above 0.7. Now you might say to yourself, okay, well I guess the limit's 0.7. But again, that's an approximation. The limit is close to 0.7, but not exactly. So obviously the graphical approach, this is a perfect example where the graphical approach doesn't work well. Then you might say to yourself, okay, well, what about if I try the numerical approach? Well, here is the numerical approach. Right below, you have a table of values. And so what I have done is looked from the left and the right, and as x values get very, very close to 0 from the left and from the right, and you see the same thing. Like obviously it looks like the y values are getting closer and closer to 0.7, maybe 0.707, but it's hard to tell like, well, what's the exact limit, because we don't see that, we don't have this obvious limit like 5 or 1/2 or 10 or 0 or whatever. It's a decimal approximation without an immediate recognizable solution. Unless you've been thinking about trig a lot lately. And if you've been thinking about trig a lot lately, you might think to yourself, oh, 0.707, that kind of rings a bell. Turns out the actual limit is 1 over square root of 2. But I would hazard to guess that nobody in this class probably would have recognized that if I had to guess. Maybe one person out of 30, 35 students might recognize that, but maybe not, okay? Because I've done this before in live classes and nobody recognizes it. I'll have 30 or 40 students sitting in a classroom and nobody recognizes what the limit is. So that is obviously a drawback to the numerical approach, and it's the same drawback that we had to the graphical approach. So we need a better way, and analytic methods, that is the better way. Okay. Now, to do that, we need some properties of limits. Properties of limits, and that is theorem 1.4.1. Super important. We will use these periodically throughout the rest of the class. And in fact, if you're going on to more calculus classes, Calc 2, Calc 3, you'll need these properties in those classes as well. Okay, so let's just take a look. I'll constantly refer back to these, and we'll use these in especially the near future videos. We'll be constantly coming back to these and say, okay, constant multiple rule, product rule, quotient rule, et cetera, et cetera. So, we'll just briefly talk about them now, and then we'll show them in action very soon. All right, so the constant multiple rule. This says if you have a limit of a function times some constant, that you can factor out that constant out of the limit, and then take the limit of the variable portion of the expression. Okay, sum difference, sum or difference. I call it sum difference just for short. Basically says if you're adding or subtracting two functions, and you want to take the limit of that sum or difference, then you can actually take the limits individually. So instead of taking the limit of a sum or a difference, you can take two individual limits and then add or subtract the results. Okay? A very similar property for the product rule. The product rule says that if you have if you're taking the limit of the product of two functions, and it for some reason is easier to take the limits individually, then you can do that and then multiply those two individual limits. So you take the limits individually, multiply the results, and that is equivalent to the original statement. Quotient rule, very similar. Now the quotient rule, you do need to assume that the denominator here, that limit is not equal to 0, but barring that, you can take the limit, if you're looking at the limit of a quotient, you can take the limit of the numerator and denominator individually. Again, provided the denominator, that solution to the limit, is not equal to 0. Okay, and then a last one here, we have a composite property, which says if you're taking the limit of a composite function, compositions when you have an outside and an inside function, that you had a lot of practice with in college algebra, maybe pre-calc too. If you have a limit of a composite function, you can instead take the limit of the inside function, get that answer, and then evaluate the outside function at that limit. Okay, we'll use all of these a good bit when we're trying to solve a limit analytically. And analytic results, again, like I said, is probably the analytic methods are probably the most important part of this chapter, because this is what we're going to use on a regular basis going forward when we need to find a limit. Okay, because when we need to find a limit, the numerical approach and the graphical approach are usually not very good. They're important, yes. It's important that you know how to use them. That, for instance, a numerical approach is a good backup, like it'll confirm your answer. And it's always a good idea to have a really strong graphical intuition in calculus class. So knowing how to find a limit graphically is important, but analytic methods are the most important because these are like the surefire way to get an answer. You can get exact answers without having to worry about approximations. And this will be the biggest part of your first test. So you really want to put a lot of time and attention into analytic methods and the properties of limits. That's the first part of that. Okay, so let's look at a couple examples. Actually, let's first talk about your first approach. If you're tasked with finding a limit analytically, your first approach should always be this. Right here, direct substitution. Now, I'll tell you this, it's almost always going to fail. Direct substitution is almost always not going to work, but it should be your first choice, because if it does work, then it's the simplest way and it's easy. As long as you're careful with your arithmetic and such. But you should always use direct substitution first. But again, it's almost always not going to work. But here I have 4 examples where it is going to work. Okay, and we'll talk about why it works in just a sec. So let's see here. Example A. Example A is the limit as x goes to 1 of x squared plus 3x. Now, when I say direct substitution, what I mean is we substitute that value of c. Remember, we call the value you're approaching, that's the value of c is what we refer to it as. Limits as x go to c. So, all those c's right there, I call that the value of c, the 1. So all you have to do is plug in c. Okay, substitution. So let's see, we have the limit as x goes to 1 of x squared plus 3x equals, okay, let's see if direct substitution works. Now, what I mean by works is, well, if you try to plug in a 1, does it cause any problems? Like domain type problems. Does it cause division by 0? Does it cause a radical of a negative number? Because we're only dealing with real numbers in this class. We're not dealing with any imaginary numbers. So I think if we plug in a positive 1, nothing bad happens algebraically. So we can just say, well, it equals, I'll plug it in, 1 squared plus 3 times 1 equals, well, that's 1 plus 3 equals 4. So the limit is equal to 4. Easy peasy. What about B? All right, in this one we have, let's see here, let's separate that off. We have the limit as x approaches 0 of a quotient, x plus 1 over x plus 2. Now, technically, I should have maybe showed this in the first example. Technically, what's happening here is we're applying properties of limits. And I should have done this in the first example, so I apologize. Maybe I'll go back and do that in just a sec. I kind of got ahead of myself. Now, what is the property that applies here? Well, it's the quotient property. Now, what this says is, okay, you can take the limit of the numerator and denominator individually. So we say the limit as x approaches 0. Oh, let's fix that. Of x plus 1 over the limit as x approaches 0 of x plus 2. And those do need parentheses since there's multiple terms. And now we can say to ourselves, okay, well, that's an easy limit to take. I can just use substitution. So on the top, we get 0 plus 1, and on the bottom, we get 0 plus 2, and that gives us overall 1/2. Okay, here, let me back up and do example A again to show the property that's necessary. So technically here, we have the sum of 2 functions. So we're going to use the sum or difference rule right here. Technically, well, specifically, we're going to use the sum version, the addition version. Okay, so this says we take the limit of those 2 terms individually and then add the results. So we have the limit is x approaches 1 of x squared plus the limit as x approaches 1 of x. And now we say to ourselves, okay, I can take those 2 limits individually. I plug in a 1 for both of them, and we get 1 squared plus the other one is 3 times 1, which is the exact same thing we had before, gives us 4. Okay, but it's the sum difference rule that allows us to take the limits of those 2 functions individually. Same thing here with C. C, we have a little trig. Don't let that bother you. If we can use substitution, then just go ahead and do it. But let's show the limit properties in action here. I'll just start with C. I already have it written right there. Now I'll save myself a little bit of time rewriting. Limit is x approaches pi. Again, we have the sum of 2 functions. We have the sum of sine x plus the limit as x approaches pi of 4 times cosine x. Now, there's actually another property at play there. The additional property is that we have a constant multiple. So we can say this is the limit as x approaches pi. Leave the first limit alone, sine x, but we can factor out that 4. That 4 is a constant multiple, a scalar. So we can factor it out of the limit. And we have just cosine, the variable portion, left over. Let's erase that page number. Let's see if we can do that. We can erase by finding a white. There we go, a white pen. All right. Let's see here. And now we can say, all right, we have two limits. I can evaluate them individually, and we get, well, the first one is sine pi plus 4 times cosine pi. And again, the reason I can do that is because I know that sine and cosine both have domain all real numbers. So I can plug in any number I want, and it's not going to cause any problems. And pi is completely okay. What's sine of pi? So make sure you know your unit circle. You have to know your unit circle throughout this class. Sine of pi is 0. Plus 4, what's cosine of pi? That's -1. So we get -4. Okay. Oh, let's see here. Equals for part D. We have the difference of two functions. So again, we're using the sum difference rule, and we take the limit of each of those terms individually. Okay, and now we simply evaluate via substitution. Now do be careful. Oh, I said 1. Why did I say 1 there? I'm not really sure. We replace those 1s with what it's supposed to be, 9s. X approaches 9. Now, the reason I included this one is that, okay, what is it? We're trying to use substitution here. What does it mean to plug in a 9? You're plugging in 9, but what are you doing? You're plugging 9 into a constant function. So whether you're plugging in 9 or 900 or 9 million, whatever you plug in for the input, the output is always 1 because it's a constant function. A constant function means that regardless of the input, the output is always the same, which in this case is 9. Minus, okay, plug in 9 here, log base 3 of 9. Okay, we got to remember how to work with logarithms here. What is this asking for? Okay, just off to the side, just to remind you, log base b of x equals y. That can always be rewritten in an equivalent form of b raised to the y power equals x. In other words, this is asking us 3 raised to what power y equals 9. 3 raised to what power equals 9? Well, obviously that answer is 2. 3 squared equals 9, so log base 3 of 9 is 2. And then we are on our way because 1 minus 2 gives us -1. Okay? Now, the moral of the story is that we can evaluate limits using direct substitution in some cases, and if you can, that is the best approach. But I will warn you that it almost always doesn't work, and you'll see that in all the following videos. Okay, in fact, the last example for this video, you'll see that. So let's talk about this theorem in one more example. So theorem 1.42 kind of talks about why we could do those previous limits by just using substitution. So why those 4 limits worked out nicely. Theorem 1.42 says basically if you have a pretty typical function, constant, polynomial like example A, rational like example B above, trigonometric like example C above, logarithmic like example D above, exponential. And if you have any of these, I call them typical functions, rational, radical, trigonometric, exponential, logarithmic, polynomial, if you have any of those functions, and the function is defined at x equals c, in other words, c is in the domain of the function, then to evaluate the limit, all you have to do is use direct substitution. And that is what we did above. We simply use direct substitution. Now, pretty soon we'll have a word for this characteristic, and it'll be continuity. We'll say that if the function is continuous at x equals c, then the limit as x approaches c of f of x equals f of c. But we're not quite there yet. We'll talk about continuity in the relative near future. But we can just, for the time being, say if it's in the domain of the function, if the value of c is in the domain of the function, and we're working with one of these typical functions. Okay. Now, if you get some weird functions like piecewise that we've seen before, this theorem 1.42 does not hold. Okay, it holds for these functions I have listed here: constant, polynomial, rational, radical, trig, exponential, logarithmic, and the function has to be defined at c. That is, c has to be in the domain of the function. But theorem 1.42 basically allows us to use direct substitution if it works. Okay. Now, let's consider a situation where this theorem 1.42 does not work. So it did work for the 4 examples up above, and let's look at one example where it does not work. So, example 1.43. If I try to use direct substitution, which it should always be my first choice, I get the limit as x approaches 0. So I'm just going to rewrite of x over x squared plus 2x. If I try to evaluate with direct substitution, I would say equals 0 over 0 squared plus 2 times 0, which is 0 over 0. Okay, that is what we would conclude at that point, that we have indeterminate form. We've seen this before. Indeterminate does not mean that the limit does not exist or that the limit does exist. It means you're unable to determine what is going on in terms of the limit. Okay, so this is what it means when I said that direct substitution sometimes does not work. So if you get a situation like this, we would just say direct substitution fails. It doesn't work. And this is a very common mistake that especially first semester students make, is they say, oh, division by 0, I guess that means the limit doesn't exist. And they just write a big D and E. Well, that could be the case. Probably not, though. So don't be tempted to say that just because we found division by 0, i.e. we found this indeterminate 0 over 0 form, don't be tempted to say the limit does not exist. That just means we have to do some further investigation. And here's a possibility. And this is going to lead to one of our first methods. Here is the possibility of what we could do. We could try to simplify the function algebraically, rewrite the function. Okay? Now, what do I mean by rewrite? Well, I mean use all of our techniques from algebra, like factoring and dividing out and all that kind of stuff, rewriting, basically algebraic manipulation. Use those properties to see if we can somehow algebraically manipulate the function so that eventually direct substitution does work. Let's see. Well, we could write this is equal to the limit as x goes to 0. Let's try to factor the denominator. If we try to factor it, we get what? We factor x out. We get x plus 2 like that. Are those two denominators equivalent? Yeah. If we try to distribute, we would get x squared plus 2x. So yeah. But now notice what you can do. Now we have a factor of x on the numerator and a factor of x on the denominator, and we can cancel them out. Here, I can do this. Okay. Now, what does that leave us with on the numerator? That leaves us with a 1 on the numerator. By the way, that's another common mistake where I see a lot of students make, is they say there's a 0 because you canceled everything off, so that means there's a 0 left there. But no, there's a 1 left there. If you cancel everything off, there's still an understood 1 there. And on the denominator, we're left with x plus 2. Okay? Now, technically speaking, these two functions are not equal. However, their limits are equal. So it would be incorrect to say that x over x squared plus 2x equals 1 over x plus 2. Clearly, those are not the same thing, but their limits are equal. And that's really important because that means we must be very careful with our limit notation and saying the limit as x approaches 0 out in front. Because if we don't do that, well, then we're claiming these two functions are equal, which indeed they're not. Why are they not equal? Well, clearly, you can't plug a 0 in here, but you can plug a 0 in there. So clearly their domains are not the same, so they cannot be the same function. Okay? Here's what we can say. We could say they are equal, assuming, oh, let's fix that. If I put like a comma there, and we are assuming x is not equal to 0. That is, if you look at all other values besides 0, they're equivalent. Like if you plug in a 1, what, you get 1 over 3? Obviously you get 1 over 3 here. Over here you get 1 over 3 too. If you plug in a 2, you get 1 over 4 over on the right-hand side. You get what? 1 over 4 on the left-hand side. Okay? Because you would get 2 over 2 squared plus 2 times 2, so you get 1 over 8, which is, or sorry, you get 2 over 8, which is 1 over 4. So these two functions are equal if you ignore all values except for 0. But in general, they are not equal. Okay? So if I erase that, I have to say they're not equal. Okay? Now, let's go back to the limit. Okay, so we have this going on, and then we're going to go over here and say, all right, well, now, is there any trouble with using direct substitution? I've simplified the function. Is plugging in a 0 going to cause any problems now? No. So now I can actually take the limit by using substitution. And notice when I do that, I'm going to drop the limit notation. So I'm taking the limit, so I drop the limit notation. I get 1 over 0 plus 2, which obviously simplifies to 1/2. Okay? So this is going to be our basic strategy for solving for solving limits analytically. So let me just summarize it for you really quickly. To solve a limit analytically, which is what our main method for solving limits going forward, the basic ideas: use algebra, or maybe trig. So let me back up because we will need trig sometimes. Use algebra / trig to rewrite the limit, and then use direct substitution. When possible. So notice we couldn't use direct substitution immediately, but after we did a little bit of algebraic manipulation, we could use direct substitution. And that's the general idea when solving limits analytically. Now we're going to have a bunch of different types of techniques to use. And here's a bunch of here's the most common ones. Factor and divide. That's what we did above. We factored and divided. That was the example of our first method. We'll have several examples in the next video. We're going to have this other method called rationalizing the numerator. Okay, you might have done something like that before, rationalizing the numerator. Then we have this other method called, let's call it general algebraic simplification. Then we're going to have some special limits that we can use. We're going to have something called the squeeze theorem. We'll have some more properties of limits, of infinite limits, sorry. And so we're going to have these, whatever, this is like 6 different basic techniques. And I'll have a video for each of these with a handful of examples in each video. And yeah, that's how we're going to proceed. But but those are specific strategies. The general strategy is just to solve a limit analytically. You algebraically manipulate it, or maybe using trig too. You manipulate it until eventually you can use direct substitution. That's the basic idea. And then we have those specific techniques in the box below. Okay? And theorem 1.43, this is the last thing for this video. That's basically what theorem 1.43 is getting at. It says if you can find a new function where that new function agrees with the original function everywhere except for at the value x equals c, then their limits are equal. And if their limits are equal, well then and g has a limit that you can take via direct substitution, well then that's the key. That's the takeaway here. Is that if you can rewrite the function and get some new function which we're calling g, and you can use that function with direct substitution, well then that limit will be equal to the original limit. Here, let's look at the graph, and I'll just show you with the example above why this works. So the idea is you're finding a new function that agrees with the original function everywhere except for a single point at the point x equals c. So let's look at this. Our original function in example 1.4.3 was x divided by x squared plus 2x. So here is our original function. Here we go. Obviously, it has an asymptote where, let's put the asymptote in. That's what, -2. So x equal -2. Let's make that dashed so we know it's not a part of the graph. It's just a visual indicator that there's an asymptote there. Okay. Now, what is our like new function? The simplified function. It was at 1 over x plus 2. Okay, so let's now graph 1 over x plus 2. And I'll do that in a different color. X plus 2, it's in purple. What do you notice? You notice that they almost look identical. Now, what did I say? Actually, I erased it. It was like right here on the page before I erased it. It said that those two functions are identical except for at what value? At 0. So let's investigate what's happening at 0. Okay, so there's the original function. And watch if I drag a point over 0, what happens? Oh, undefined. Because clearly in the original function, x divided by x squared plus 2x, 0 is not in the domain. You cannot plug a 0 in. We said the function was indeterminate at 0. However, you can clearly see there's a limit. I mean, we're approaching from the left, it looks like 1/2. Sorry, that was from the right. From the left, 1/2. From the right, 1/2. So the limit certainly does exist. And what we have done algebraically by simplifying the function is we said, hey, this new purple function matches the original blue function perfectly everywhere except at 0. And watch what happens now if we hover over 0. The y value is 1/2, which means we can find 1/2 via direct substitution. So that's what we've done. We found a new function, this new purple function, that coincides perfectly with the original function everywhere except for at the value 0, x equals 0. And that means that once we rewrite, we call this new purple function g, the limit of g of x as x approaches 0 will be equal to the limit of f of x, the original function, as x approaches 0, and they are both equal to 1/2, which we found via direct substitution on the simplified version. So again, our general idea behind solving limits analytically is to simplify using our entire algebraic and trigonometric toolbox of factoring and compound fractions and just all that stuff. And if we can simplify enough, we should eventually be able to use direct substitution, just like here with example 1.43. So the game plan for the next 4, 5, or 6 videos is to show how to use all of these specific techniques in action to solve limits analytically. But remember, the idea is common amongst all of them. We're just going to try to simplify as much as possible, so eventually we can use direct substitution. So in the next video, what we're going to do is talk about this first method, which is the factor and divide out common factors method. So basically, more examples of what we did in the previous example, which was example 1.43. We're going to do a bunch of those like that, except they're going to be harder. Maybe take a little more brain power with factoring and such. Okay, and then we'll just work our way through that list for the next handful of videos. All right, I'll catch you then. Always feel free to reach out if you need help. I'll see you in the next video.